Hello, I'm Sheldon Axler, the author of Linear Algebra Done Right. This video discusses part 2 of the section of the book titled Determinant. In this video, we will focus on change of variables in integration in Rn. Let's begin by reviewing the definition of isometry. Suppose V is an inner product space. An operator S on V is called an isometry if the norm of S of V is equal to the norm of V for every vector V. In other words, an operator is an isometry if it preserves norms. Now we come to a theorem telling us about the determinant of isometries. Suppose V is an inner product space and S is an isometry on V. Then the absolute value of the determinant of S is equal to 1. Let's look at the proof of this result. First, suppose we're in the case of a complex vector space. Recall that the determinant of S is defined to be the product of the eigenvalues of S, counting multiplicities. Because S is an isometry, we know from previous results that all the eigenvalues of S have absolute value 1. Thus, the product of all the eigenvalues of S, counting multiplicity, also has absolute value 1. In other words, we have that the absolute value of the determinant of S is equal to 1, which is our desired result. Now suppose that F is a real inner product space. As usual, we reduce the result back down to the complex case. In other words, we look at the complexification of our vector space, and it's easy to see that the complexification of an isometry is an isometry where we define the obvious inner product on the complexification. Please see the book for details. By the result for the complex case, we get that the absolute value of the determinant of the complexification of S is equal to 1. But of course, by definition of the determinant of S as equal to the determinant of its complexification, we get the desired result, completing the proof. Now let's erase the proof of that result so that we have room to display an important corollary. Here's the corollary. Suppose V is an inner product space and T is an operator on V. Then the absolute value of the determinant of T is equal to the determinant of the square root of T star T. Let's look at the proof, which is pretty easy. Recall that the polar decomposition states that there's an isometry S such that T is equal to S times the square root of T star T. Let's apply the determinant to both sides of this equation and then use the multiplicative property of the determinant, and then take the absolute value of both sides, getting the following equation. Notice we don't have to put an absolute value around the determinant of the square root of T star T, because the square root of T star T is a positive operator, and hence its determinant is a non-negative number. Now let's use the result in the first column at the bottom, which says that the determinant of S has absolute value 1, to get the following equation. And now if we look at the two parts of the equation in red, we see that we have the desired result. The absolute value of the determinant of T is equal to the determinant of the square root of T star T, completing the proof. We are aiming to explain the appearance of a determinant in the change of variables formula for integration in Rn. To do that, we first need to talk about the volume in Rn. We start that process by defining a box. Fix a positive integer n for the rest of this video. A box in Rn is a set of the form shown here. Let's try to see what's going on. We have positive numbers r1 up through Rn and a point x1 up through xn in Rn. We use these positive numbers and this point x1 up to xn to define the box shown above. To get a feeling for what's going on, first suppose n equals 1. In that case, our box is just an interval with left endpoint x1, and the length of the interval is r1. Now suppose n is equal to 2. In that case, our box is just a rectangle. The lower left-hand corner of the rectangle will be the point x1, x2, and the sides of the rectangle will have lengths r1 and r2. Now if n is equal to 3, we get a genuine three-dimensional box, and so on for higher values of n. Now we define the volume of a box in Rn with side lengths R1 up through Rn to be the product of the numbers from R1 up through Rn. Thus, if n is equal to 1, the volume is just the length of the interval. If n is equal to 2, the volume is what's traditionally called the area. When n is 3, we're at the actual three-dimensional volume. But to make things simple, we use the word volume regardless of the value of n. Now that we have defined the volume of boxes, we can define the volume of arbitrary subsets of Rn. Suppose omega is a subset of Rn. The idea is that we cover omega by a countable collection of boxes and then add up the volumes of those boxes. That's going to be too big, so we take the infimum of that over all collections of boxes that cover our set omega. If you're familiar with measure theory, you can recognize that what we're doing here is defining the outer measure of omega to be the volume of omega. Our purpose here is just to give an intuitive idea about what's going on with volume, rather than a full course in measure theory. We need one more piece of notation. If t is a function from a set omega into Rn, then we define t of omega to be the image of omega under the function t. Specifically, t of omega is a set of all elements of Rn of the form t of x as x ranges over omega. Now we come to our first connection between determinants and volumes. This theorem says that if t is a positive operator on Rn and omega is a subset of Rn, then the volume of t of omega is equal to the determinant of t times the volume of omega. Let me make a few comments before we get to the proof of this result. Here we're talking about a positive operator, which means we need to have an inner product in mind. The inner product we have in mind here, and for the rest of the video, is the standard inner product on Rn. My second comment is that since we are proceeding on an intuitive basis rather than a rigorous basis, you can think of omega as a smooth set with a nice boundary, if you wish to do so. Now let's look at the proof for this result. To get a good feeling for it, we will first consider the special case where lambda 1 up to lambda n are positive numbers, and t of x1 up to xn is lambda 1 x1, comma, up to lambda n xn. This operator stretches the jth standard basis vector by a factor of lambda sub j. For this operator, the eigenvectors are the standard basis vectors, and corresponding eigenvalues are lambda 1 up to lambda n. Thus, if B is a box in Rn, with side lengths R1 up to Rn, then the image T of B is also a box in Rn, but now with side lengths lambda 1 R1 up through lambda n Rn. In other words, T just stretches the length of each side by a corresponding lambda j factor. Note that because the eigenvalues of T are lambda 1 up to lambda n, the determinant of T is just the product of those eigenvalues. Thus, the determinant of T is equal to lambda 1 times lambda 2 up through times lambda n. Now the volume of T of B is the product of the numbers in the last line of the first column. In other words, the volume of T of B is equal to the determinant of T times the volume of B. We have this equation for every box B in Rn. Now the volume of T of omega is determined by the volume of boxes. We've just seen that T changes the volume of boxes by a factor of the determinant of T, and thus T has to change the volume of any set by the same factor. In other words, we have the equation now shown here. This completes the proof where T has the special form of the operator shown in the first column. Please pause the video and make sure you understand the special case well, because it is the heart of what is going on here. Now consider the case of an arbitrary positive operator T on Rn. By the real spectral theorem, there's an orthonormal basis E1 up to En of Rn and non-negative numbers lambda 1 up to lambda n, such that T stretches the jth basis vector by a factor of lambda sub j. In the special case we considered in the first column, E1 up to En was the standard basis for Rn. Regardless of whether we have the standard basis E1 up to En or an arbitrary orthonormal basis E1 up to En, this operator stretches the jth basis vector by a factor of lambda sub j. In other words, this is really the same as our first special case, except we're just using a different orthonormal basis. Your intuition should tell you that T multiplies volume by a factor of the product of the lambdas, which again equals the determinant of T. This completes the proof. Well, actually, it's a pseudo-proof with a bit of hand-waving, but it really is what's going on, and you should have a good, intuitive idea of why this theorem is true. In the last slide, we saw what positive operators do in terms of volume. Now we turn to the question of what isometries do. Here's the result. Suppose S is an isometry on Rn, and omega is a subset of Rn. Then the volume of S of omega is equal to the volume of omega. In other words, isometries do not change volume at all. I'll give two proofs of why this is true. Actually, they're not quite proofs, but explanations that should convince you and provide good intuition. For the first proof, suppose x and y are vectors in Rn. Then let's look at the norm of S of x minus S of y. By linearity, that's the norm of S applied to x minus y. And because S is an isometry, that's the norm of x minus y. Now let's highlight in red the first and last entries in this series of equations, and we see that S does not change the distance between points. And that should convince you, perhaps, that S does not change volume. But if you need a more convincing proof, let's look at proof number 2. For our second proof, we will use our complete description of isometries on real inner product spaces. We discussed this description of isometries in a previous video. That description says that an isometry can be decomposed into pieces, each of which is of a particularly nice form. We have 3 different kinds of pieces. The first is a piece in which the isometry is the identity on some subspace. Clearly, applying the identity does not change the volume. The second kind of piece we have in an isometry is multiplication by -1, or the negative of the identity operator. Again, that clearly is not going to change the volume of anything. And the third piece was rotation on 2-dimensional subspaces. If you think about what rotations does, putting them together, again, that will not change the volume. Thus, using this decomposition, we can quite easily convince ourselves that isometries do not change volume, which is what we wanted to prove. We have shown how volume changes under positive operators and under isometries. Now we can put those results together in a very pretty way to show how volume changes under an arbitrary operator. Here's the result. Suppose T is an operator on Rn and omega is a subset of Rn. Then the volume of T of omega is equal to the absolute value of the determinant of T times the volume of omega. Let's look at the proof of this result. We'll use the polar decomposition, which says there's an isometry S such that T is equal to S times the square root of T star T. Thus T applied to omega is S applied to the square root of T star T of omega. This means that the volume of T of omega is the volume of S applied to the square root of T star T of omega. But we proved earlier in this video that an isometry S does not change volume. So we can get rid of the S, getting the equation shown here. The operator square root of T star T is a positive operator, and we've shown earlier in this video how that changes volume, namely by the determinant of the square root of T star T. So we now have the equation shown here. We've also shown earlier in this video that the determinant of the square root of T star T is equal to the absolute value of the determinant of T. And now if we look at the 2 items highlighted in red, we see that we've proved exactly the result that we wanted. Now that we've had a good discussion about volume, we can move on to integration. What follows is meant to convey the ideas of what's going on, rather than to be strictly rigorous. Suppose omega is a subset of Rn, and f is a real-valued function on omega. The integral of f over omega is denoted using either of the two notations displayed here. The integral is defined by breaking omega up into small pieces. On each of those small pieces, we assume that f is almost constant. Then on each piece, we multiply the almost constant value of f by the volume of that piece, and then we add up all those numbers for all the pieces, and that gives us an approximation to the integral. This approximation becomes more accurate as we divide omega up into smaller and smaller pieces, and then taking the limit, we get the integral. This procedure should remind you very much of the Riemann integral that you learned about when taking calculus. Let me add two comments about this definition. First, the omega in the definition needs to be a reasonable set, meaning perhaps open or perhaps measurable, and f needs to be a reasonable function, perhaps continuous or perhaps measurable. The second comment is that if you look at the notation displayed in the left, the second notation used for the integral over omega of f of x dx. In that notation, the x is just a dummy variable and could be replaced by any other symbol. Having dealt with integration, we will now deal with differentiation, and then we'll come back and connect the two concepts. Suppose omega is a subset of Rn, and sigma is a function from omega to Rn. The function sigma is called differentiable at a point x in omega if there's an operator sigma prime of x on Rn such that the limit that you see here is equal to 0. Let me mention a few points about this definition. First, we probably want omega to be a nice set, maybe all of Rn, or at least an open subset of Rn. Second, the limit as y goes to 0 is taken for vectors y in Rn. Third, let's make sure the objects shown make sense. Sigma prime of x is supposed to be an operator on Rn. So in the numerator, when we have sigma prime of x applied to y, we get a vector in Rn. Thus the numerator really does make sense. The idea of this definition is that for x fixed and y a vector such that the norm of y is small, sigma of x plus y should be approximately equal to sigma of x plus sigma prime of x applied to y. In other words, the numerator should be small. Notice that it does not make sense to divide by a vector. Thus, we really need norm y in the denominator above. It would not make sense to write just y there. If n is equal to 1, so we have a real-valued function sigma on some interval on the real line, then the connection with the usual notion of derivative is as follows. Sigma prime of x, as defined here, is the operator from r to r of multiplication by the classical standard derivative you learned in calculus. Let's return to the situation where omega is a subset of Rn and sigma is a function from omega to Rn. For each x, we can write sigma of x as sigma 1 of x up to sigma n of x. Here, each sigma sub j is a function from omega to r. The partial derivative of sigma sub j with respect to the kth coordinate is denoted d sub k of sigma sub j. Evaluating this partial derivative at a point x in omega gives the notation d sub k sigma sub j applied to x. Now here's a theorem, not very hard, but we're not going to prove it here. If sigma is differentiable at x, then the matrix of sigma prime of x, remember that's an operator on Rn, the matrix of sigma prime of x with respect to the standard basis of Rn consists of dk sigma j of x in row j, column k. In other words, the matrix of sigma prime of x is as shown here. If this is new to you, you may want to stop the video and think about it, or look in a book to see further explanation about this. Now we have the payoff for the work we've been doing. Suppose omega is an open subset of Rn, and sigma is a map from omega to Rn. Suppose that sigma is differentiable at each point of omega. Suppose f is a real-valued function defined on the image sigma of omega. Then we have the integral formula shown here. Notice that in the integral on the left, we're integrating f over the set sigma of omega. To get to the integral on the right side, we can think of making a change of variables in the left side by replacing w with sigma of x. Then we're integrating on the right side over omega instead of sigma of omega, and the function we're integrating is f composed sigma of x, and to make the formula come out right, we have to throw in the factor of the absolute value of the determinant of sigma prime of x. Let's look at the proof of this result. Again, we're more interested in understanding why it's true than completely justifying each step. So fix a point x in omega and let capital gamma be a small subset of omega that contains x, such that f is approximately constant on the set sigma of gamma. So f will be approximately f of sigma of x on this set. Now, we have an approximation that comes from the definition of the derivative sigma prime of x, and it's shown in the last line in the first column. In this approximation, think of x fixed, and think of y as varying over a small set so that x plus y varies over the set capital gamma. We're interested in estimating the volume of sigma of gamma. For this approximation formula, sigma of x is just a constant, and translating a set by a constant vector does not change the volume. So we get the new approximation shown in the right column. The volume of sigma of gamma is approximately the volume of sigma prime of x applied to gamma. Now sigma prime of x is an operator, so we know how to find the volume of it applied to a set, and we get the formula shown here. This uses the formula that we derived earlier in this video. Now we're ready for the change of variables. Let w equal sigma of x. Multiply the left side of the equation above by f of w, and the right side by f of sigma of x. Those two things are equal because w equals sigma of x, and we get the equation now shown here. That's essentially the formula we want, because we can break omega up into many small pieces and add the corresponding versions of the equation above, getting exactly the desired result. You should pause the video and think about this proof to make sure you understand what's going on. By the way, the change of variables formula shown here in the blue box seems to me to be one of the few legitimate uses of the determinant in the undergraduate curriculum. We did not need to use the determinant to prove the existence of eigenvalues or to define the characteristic polynomial. Determinants do have important uses in more advanced mathematics, but not so much in the kind of linear algebra we've been discussing. However, this change of variables formula is an excellent application of determinants. You should look in the book to see two nice examples of this change of variables formula. Those two examples are integration in polar coordinates and integration in spherical coordinates. These formulas are useful in computations, so let's wrap up this video with a portrait of Ada Lovelace, who is a pioneering British computer scientist and mathematician from the 1800s. This concludes what is currently the last video in the series of videos to accompany linear algebra done right. I hope that you have enjoyed these videos and found them useful. If you want to be notified about any future videos, you can do so by subscribing on YouTube to this series of videos, or by following the book at Twitter. The Twitter address is @AxlerLinear, or you can check the book's website. It's www.linear.axler.net. Best wishes as you continue to learn more about linear algebra. Bye-bye.